Hey everybody, thanks for joining me for another edition of Mondays with Mike. And today is going to be, I hope, an interesting one. And I'm going to pose a question to you to begin. Okay, so here we go. Stay with me. What does this ball have in common with The Price is Right and hurricanes? See, I should be playing the Jeopardy theme there. Well, the answer is we could use them all as an example of how hard it is to track the movement of something the farther out in time you go. All right? What in the world is Mike talking about? Well, let's get into it, okay? So we're talking about the tropics. I haven't something come up on the screen there. We're talking about the tropics and the fact that, over the last few days, and you may have even seen posts online, over the last few days, there have been some, people have been posting things they probably shouldn't be posting, and that's what this is all about. So basically, we have several computer models that we use. Some of them are very short term. They go out like 18 hours, okay? Some of them go out 48 hours. Some of them, now the American model, the GFS model, Global Forecast System, it goes out 16 days. Now, it's really useful to be able to see something go out 16 days, but what you cannot do, and I'll explain why, is to take one of the days, let's say day 14, and it shows something significant happening over Houston or somewhere nearby. You can't take a snapshot of that, one model run, 14 days out and say, oh my gosh, look at that. Because there's a lot of error that goes into it that is a result of going that far out. And so if you see anything posted online where, let's say, well, today's the 16th, right? If you see somebody post a computer model output that's for the 29th of May and it's showing something catastrophic happening here, sure, there's a small chance that's going to happen, but the odds are, as you get more computer models, more, a little bit closer, more runs, whatever situation they were posting is going to change a lot. And so it's really irresponsible for some of those people who are mostly not professional meteorologists to post that stuff online. So it's just kind of a lesson that, as we'll learn here, you'll want to go with trusted sources for information. All right, so let's get into it. I mentioned The Price is Right. I mentioned this ball. What does that have to do with this? Okay, what does that have to do with something forming? Well, we're going to start out talking about the game Plinko. Okay, now just so you know, The Price is Right did not invent this game. I mean, this is actually used in mathematics to show what's called a normal distribution. Remember that bell curve from school? There was always that teacher that wanted to grade everybody on this bell curve. I didn't like that because I thought if everybody did A work, everybody should get an A. But there was this belief years ago that everybody should get a C. The majority of the people should get a C, and then there's this bell curve. Some people get an F, some people get an A. I don't believe in that. But with Plinko, okay, so you remember with Plinko, right? In Plinko, you would win a certain number of these little discs, right? And then you could they would climb to the top of this platform and you would look down on something that looks like this, okay? And down here would be money that you could win, right? So I think the middle was 0, and then you'd have 10,000 or 1,000 or whatever it was. And then other amounts. So the person would go up here and would always try to decide where to put the ball, right? And it's hard to figure out where to put it, right? Because why? Well, let's just say there were no plinks, okay? There were no little metal barbs pointed out. Well, then where would you put it, okay? You would find the highest dollar amount, right? Let's say that was $10,000, and you would put the Plinko chip up there, and you would just drop it straight down because it would be very easy to see where it's going to go, right? You would just drop it straight in to the one with the biggest money. But the way this is designed, okay, the way it's set up, is that as soon as you let go of the Plinko disc, okay, think about this maybe as a hurricane, okay? As soon as you let go, it's going to hit this first little bump, and it could either go that way or that way, okay? So that's one problem. It has a 50% chance of going left or right. Then once it gets over here, it has another 50% chance. Then over here, another 50% chance. So what happens is you have all of these different outcomes from this one starting point, okay? So what you could do, right, one thing you can do is if you were able to measure the exact starting point of the Plinko chip, I mean, as well as you could possibly measure it. How fast is it going? What angle is it hitting the first little plink, okay? Then, and you had a supercomputer, okay, then you could probably get a better idea of whether or not it's going to go left or right initially, right? So that's good. And then maybe even the second go around, you would have a better idea of whether or not it's going left or right. So now we could maybe predict a little bit better step 1, step 2, step 3. We would have a better idea. Think about that like a hurricane forecast, okay? We're talking about forecasting a swirl of winds, or sometimes even something that hasn't even formed yet, right? Just maybe a tropical wave. And the computer models are trying to figure out so many things, like how strong it's going to be, how large it's going to be, the pressure, the humidity, the winds, all of that stuff, and where it's going. So it's very complicated, a lot more complicated than Plinko. But it's the same kind of concept, okay? The better we can model or measure the start of the Plinko chip, the better we can figure out where it's going to go in this range. But just like the Plinko game, when you start going out to day 10 or day 11 or day 15, okay, on a computer model, you're going to have a wide array of solutions, okay? And it'll get less and less accurate typically, okay? Because of all of these little decisions that it has to make, okay? Now this goes back to some mathematical work that was done by a guy named Lorenz, L-O-R-E-N-Z. And a lot of times it's sort of taught, or you'll hear the term butterfly effect, right? Where a butterfly flaps its wings in the Amazon rainforest and it causes a tornado in Kansas or whatever, which probably is not true, but the concept is valid, it's correct, and it's called sensitive dependence on initial conditions. Okay, sensitive dependence on initial conditions. What it means is that depending on where you put the Plinko chip, it has a huge impact on where the chip ends up landing, okay? But even if you take the Plinko chip and you move it just an inch to the left or an inch to the right, or maybe a centimeter left or right, or maybe even a millimeter to the left or to the right, it will have a cascading effect on where the Plinko chip goes, okay? So what in the world does this have to do with hurricanes? All right, well, what it means is that if you're forecasting 10 days out, okay, and as the hurricane gets tracked, okay, let's say the blue line is the computer model forecast, and the green line is what actually ends up happening, okay? At the very beginning, okay, they're close together. So let's say this is like the first day, the second day, the third day. The model's going to be pretty close to where the storm ends up actually going. But once you go out farther, there's this really wide range, which is why, you know, when we show hurricanes, what do we show? The cone of uncertainty, right? Because the average error in the forecast for 72 hours out, the 3-day error is 100 miles, okay? 100 miles, if you imagine this is the cone of uncertainty. See how the hurricane has to do with Plinko, okay? This is just like a cone of uncertainty. And it's about 100 miles average error for 72 hours out, okay? 120 hours out, which is 5 days, it has about a 200-mile error, roughly. So if you're looking at a 5-day forecast, you have to still figure that anywhere from Corpus Christi to New Orleans, you know, or maybe even more than that, like Brownsville to New Orleans, that whole area, even if we're in the middle of a hurricane track, that whole area is within the bounds of the forecast error, okay? Sometimes the error is less, sometimes the error is more. But Hurricane forecasting is just like the game of Plinko in that there is a cone of possible results. And so that's what the price of right has to do with hurricanes. All right. And I'm going to show you this ball in a minute. As far as where storms form in the month of June, June's right around the corner, right? Well, 2 weeks away. So when we do have storms forming in June, they tend to be right at our back door, right at our footsteps, if you will, in the Gulf of Mexico, mostly because the water's pretty warm there, and sometimes the winds are a little bit more favorable. If they don't form in the Gulf of Mexico, they form this area here, which is the Western Caribbean. So Yucatan storms, and then also down here by Honduras and Nicaragua. Also, occasionally they could form off the east coast of the United States. Those are the ones that very rarely affect us because these will go straight back out into the Atlantic. So these are the three regions when we look at the month of June of where storms can form. All right, so back to Plinko and this ball. I like this ball. It's a squeeze, it's a stress ball, but it's also in the shape of the earth. So I'm going to hit stop here, and I'm going to switch the camera around because I want to show you how this ball is very similar to tracking hurricanes. All right, so I've come out here to the beautiful Fox 26 atrium, a place where I haven't actually been here for a long time. We used to do morning show, like live shots out here. We would have bands. I mean, this is all pre-COVID stuff. But anyway, why am I out here? Well, I needed an open space where there was nobody looking at me. That's the main reason why I'm here, because I was embarrassed here holding a phone, talking into the phone. I guess people do that all the time, but you know what I mean. What does a ball, this ball, have in common with the Plinko game and with tracking hurricanes? Well, it's the same reason that playing sports is hard. Because it's hard to know exactly where a ball is going to go. Okay? If I were to drop this ball right now, okay? If I were to drop this ball, it would be pretty easy to figure out where the ball is going to go initially. Let's say for the first few seconds or tenths of a second. I mean, it's going to go straight down, basically, okay? Unless I threw it. But if I let go of it, it's just going to drop straight down. Let's see. Okay, here we go. You ready? 3, 2, 1. All right. I have dropped the ball, and it rolled way over here. Let's try that again. So I'm going to try to drop the ball exactly the same way. Now it went that way. It was over here last time, and now it's here. Okay, so I'm going to try to drop the ball the exact same way again. And now it didn't move very much at all. Well, now it is moving. All right, has Mike lost his mind? What are you getting at here, Iscovitz? Get to the point. Why are you bouncing balls around the atrium? Well, think about it. Tracking this ball is really similar to tracking hurricanes, okay? At the very beginning, we have really high confidence as to where the ball is going to be. You drop it, it falls basically straight down. Maybe I didn't drop it the exact same way every time. Maybe my finger caused it to roll or something like that. But overall, it's pretty accurate at the very beginning, even if we don't have a computer model, right? Even if it's just us. Pretty accurate to know it's pretty much going to fall straight down until it hits the ground, right? Now, why do we have so much trouble figuring out what's going to happen after it hits the ground? Okay? If you're watching a football game, and I mean American football, it's even more complicated because the ball isn't round, right? I mean, the ball's pointed, which introduces a whole other challenge. But these are the best athletes in the world, right? And when somebody fumbles the ball, how hard is it for them when the ball's bouncing around and all that? How hard is it for them to pick it up and start running with it? It's actually pretty hard, which is why a lot of times there'll be another fumble or there'll be a scrum, kind of scramble for the ball. And the reason is that even in our minds, we can't calculate at that moment. There's so much uncertainty, right? Too many variables. So if somebody drops the ball initially, you can see where it's going, okay? If somebody fumbles the ball, it's very easy to see where that ball is going. But the longer you let the ball travel, the less and less accurate your prediction is going to be of where the ball is going, okay? And it's the exact same thing with this. The exact same thing with this. I mean, I could throw it over my shoulder. I'll try to throw it the exact same way every time, and you know it's going to land in a different spot every time. That is sensitive dependence on initial conditions, the so-called butterfly effect, which is why long-term hurricane forecasts, long-term weather forecasts are always going to be less accurate. The farther you go out, the more room for error. You can't measure everything, okay? If we could measure this ball, okay? Let's say we had a computer model. And I said, we are gonna map this ball, every little nuance of the ball. This little seam that goes down the middle, we're gonna model that. I mean, we're literally gonna model like this thing down to just fractions of a millimeter, okay? And so now that's in our model, just like we would do with the Earth, okay? And then we're gonna map the ground. And we're gonna completely map what it looks like with all of its imperfections. And we're gonna measure the wind in the atrium. And we're gonna measure my hand and how it's releasing the ball. I dropped the ball. We're gonna measure all of that. Well, it turns out that no matter how hard we try to measure everything, no matter how accurately, we can never measure it accurately enough to model something too far into the future. Now, the more accurately you can model it or measure it, the more accurately you can measure all the variables, the more accurate your model is going to be farther down the line, okay? So the more perfectly we could use our satellites and our, all of our surface observations, radar, everything, boats, airplanes, the more information we could get crammed into the computer model, the better. But keep in mind, there's always going to be an error. I mean, think about if you were measuring the temperature. If somebody says, how hot is it outside? What's the temperature outside right now? And I might tell you it's 85 degrees. But it isn't really 85 degrees, okay? It might be 84.9 degrees. But it's not really 84.9 degrees because it might be 84.93 degrees. You see what I'm getting at. It's not even 84.93 degrees. I mean, you can measure that out to so many different, level of accuracy. So you take that error, the fact that it might not be 85, it might be 84.923 degrees, and you multiply that times a million observations, a million different pieces of data coming from all over the place. Each little piece of data, okay, has its own teensy error, and we don't know if it's, an error one way or the other. And I think you could see that adding up all those teensy errors means that at the very beginning, we'll probably know where the hurricane is. We know where the ball is going to be. We know where the Plinko chip is going to be at the very beginning. But the farther out you go, all of those errors start to really add up. It's known as the butterfly effect, the Lorenz effect, or sensitive dependence on initial conditions. And so the next time you see somebody post a day 13 or a day 14, a 2-week long forecast for any hurricane, take it with a grain of salt. figure out who's posting that. Is it a real meteorologist? Is it somebody who's just trying to get clicks? Is it clickbait? Is it just sort of some dude in his living room who's just trying to scare people? So make sure you get it from trusted sources, because the truth is, I don't care how good the model is, 2 weeks out, it's not going to get it perfect. Sorry, my alarm went off and just shut down my video. The GFS model, the American model, is just a wonder of software engineering and hardware engineering. It's run on supercomputers, and it's taken now a couple of decades to develop. It's amazing what it can do. It models the entire Earth, layer by layer by layer, from the ground all the way up. It models the entire Earth. It's an amazing thing, but even that is not going to always be 100% accurate. I will tell you though, that when you see consistency in a model, in other words, the model runs at midnight and let's say it shows a hurricane. Then it runs at 7 a.m., shows a hurricane. Then it runs at noon again, shows a hurricane. Maybe it's in a different spot, but it keeps showing it day after day after day. It definitely catches my attention. So as your Gulf Coast Weather Authority, all of us are going to be closely watching the Gulf of Mexico as we head into the late part of the month of May. So I hope this didn't bore you too much, but you probably will never watch the game of Plinko the same way again. Thanks for joining me on Mondays with Mike. See you next week.